computer. All right. Oh, and before I forget again, Lindsay is here. Lindsay is one of our data science instructors. Actually, she was on the Houston team as a data science coach, right, Lindsay? Okay, yeah, so she's just kind of observing and stuff like that. But Lindsay, feel free to like, chime in too and stuff like that. Lindsay is full of knowledge as well as all the other instructors too. So yeah, feel free. Don't feel like you have to be a silent observer, Lindsay. All right, so today, so this is kind of a mix of like office hours, right? So I want to make sure like if you guys have any questions from like your projects and stuff like that, be able to ask them. But also I have a little bit of kind of like semi-lessons. It's a little less structured, but the idea is that we'll talk about that CNN that we talked about last time. Like I showed you guys a little quick lesson on what that looked like and like what that kind of process might look like to iterate over a model and think about like a baseline model and stuff. But first of all, does anyone have any questions about anything on the mod project or come across in the curriculum if you guys are catching up through it? No? Okay. Give me thumbs up, thumbs down. How are we doing on the project right now, progress-wise? Like, feeling pretty comfortable where we're at? Like, oh, we're like, I got some problems I have to solve, or like, oh man, I haven't started. Yeah, all right. I saw a couple of thumbs up. I went through the details of that, and now some of those thumbs up have kind of turned this way, which is good. Like, I mean, I think that's good that you're having like a little bit of problems. I used to have a high school teacher that would say, like, my goal for you guys is to get you guys stuck. And like, because the things that you get stuck on when you're like this are things you're gonna remember a lot more. So that's I wouldn't call that like a negative thing at all. But I think everyone at this point has started to, and I think if I have this right, yeah, everyone has already told me what project they're working on. I think most people are working on either the image recognition one or the NLP. I think we're, at least, I don't know, maybe this isn't true. I was gonna say we're slightly skewed towards the image recognition one, but that might just be because those people have the most questions. I don't know. Not that to say like you shouldn't have questions. I just think it's a different kind of data set. So let me go ahead and pull up a window and we'll just talk about, yeah, there's no questions. So we'll just talk about that lesson that I talked about from before. So let me go ahead and share my screen. All right. And so, oh, where did my Zoom window go? There you guys go. So I can see all your guys' smiling faces or blank stares, which one of the two. All right. So, okay. All right. So actually, I'm not going to use this repo today because that's not what we're going to talk about. At least we might come back to it, but I didn't want to talk about this lesson in particular. Is I kind of mentioned about the traffic sign recognition, right? So good to see Alvaro nodding his head. And this one again is like kind of based around Udacity had like a project for like a self-driving nano degree, but the data basically is from this benchmark data set, basically traffic signs. I actually believe they're German traffic signs. So that's kind of like where that's kind of nice that they actually have this kind of built together. So you can actually find this repo. I think if you just literally search traffic sign recognition project Udacity, you could probably find the original repo with all the information that's publicly available. But just kind of that's what it's based around. But we're going to do something slightly different. So instead of like, I think the project itself, if you read it like on the repo, it's about just identifying the traffic signs. We're going to go into a little detail, like trying to put a little bit like almost like a mini project of like what this would look like, right? So I think one question that a lot of people do is like when they're doing this image recognition, it's like, oh, I just build a CNN and just train it, and then like that's the whole project, right? And it's like, well, if you want to be like if you don't want to put a huge amount of work into it, it's like, yeah, I guess technically. But I do think it's kind of important to like observe and see what things can we do. So I'm actually going to open this up in Google Colab, which is also the reason why we're doing this guy here today. And let's see here. Sorry, I'm just kind of trying to find how I can do this real quick. Sorry, I'm just getting the URL specific. I should have had this prepared for you guys, so I didn't have to type it in myself. I did have, like, you can see here, I have a little button, the Open Colab. I did not implement it correctly for some reason, so that's why I have to put in this URL directly. I guess I could have opened up Colab and opened up the exact thing, but I already finished it, so we're just gonna go with it. All right, so Colab, real quick, thumbs up. Who has use Colab so far for this project or anything else? Cool, I see some thumbs up, okay. So there's a couple things. If you have been using Colab, that's awesome. It's actually a really useful tool. It's kind of a good like intermediary between like using your own computer, local laptop, right, or desktop, and using kind of like a cloud infrastructure like AWS, Google Cloud Platform, Azure, and stuff like this. The nice thing about like something like Colab is that you don't have to really worry about like the server part. So you don't have to worry about like implementing all that stuff with Docker or like trying to spin up a new server or an instance or whatever you're trying to do. A lot of it's handled for you. So you have a less flexibility in like exactly what you hardware and structure you want to do with this specific like instance, but you can get up and going really quickly. You can kind of think of this guy, it's very similar to Jupyter Notebook. In fact, Google Colab is based off of Jupyter Notebook. But you can kind of think of like a Jupyter Notebook in the cloud. And so what that means is that this is literally going to be connected to some other computer in the cloud, and always think of in the cloud being like another computer, essentially what that is, okay, or a group of computers. So for the most part, you can actually do all your work on Colab if you had wanted to. I won't go into that full detail, but what I do want to talk about is that if you want to train a model in Colab, which is what likely, I think me and Lindsay were talking about this earlier today with another study group, is that literally like that's most of our use case for Colab is like, oh, let me just train a model here because it's free and I don't have to worry about it. That's the other nice thing about Colab is that it's free. You can still get kicked out of it in the sense that like, you know, your thing times out and basically says, oh, you have to refresh and stuff like this, but you will never get charged for it unless you pay for like the pro version. So main thing, for example, like if you are doing the image recognition, which give me a thumbs up who's doing image recognition here. I know a few people are, so cool. All right, I think everyone except for Mike. So Mike, even though it's not, this isn't necessarily for your project, it might find it useful for this project. You're using something like a deep learning model, or for future projects we're using deep learning model. But definitely for people who are using image recognition, I suggest at least using something like Colab. Probably don't use your own computer unless, I would say, unless you have a GPU, meaning that you have like a desktop most likely. And if you don't know what a GPU is, or if you, I don't know if my desktop has a GPU, it means you should be using your desktop. Probably should use Colab instead, okay? So the first thing I wanna show you guys, like this right here, you can see this connect button. Right now, this is kind of just like a file. It's not doing anything, it's not connected to anything. Kind of like there's no kernel connected when you do like Jupyter Notebook. So what we wanna do is actually connect it. So what we can do is actually click this connect here. And you'll see here it's allocating, connecting, it's initializing or something like that afterwards. And basically saying it's connecting to a computer. And so like in the cloud. And you see right here, oh good, it's connected. And you can actually see RAM and disk. So we talked about what RAM is, we talked about like your disk space and stuff like that. So we are now actually connected to like another computer, and we can actually run our stuff. Now, the thing about this though, is the reason why we're using Colab in particular is that we kind of want to take advantage of their GPU. And we talked about like why we use, we talked about what GPU is. Does anyone remember what it stands for? Just a reminder in case you guys come across this.
Graphic processing unit.
Yeah, exactly. So it's kind of like a CPU is a computational processing unit. GPU is a graphical processing unit. There's also something called a TPU, which is relatively recent, called a tensor processing unit. You can guess why it's called tensor. Is doing tensor calculations. The reason why we use GPUs is because it's more, we can do more efficient calculations with matrix multiplications and stuff, which are really, really important for some machine learning algorithms, especially neural networks, which again, why we're talking about this for image recognition for CNNs. So the thing about this though, is that you don't always by default get connected to a GPU. In fact, you have to specify this. Now, depending if I already have this set up, yeah, I already opened up this particular notebook before with a GPU hardware. So it's already defaulted, but in general, actually default to none. And basically that just is kind of like, it only has a CPU. It might have a decent CPU, enough RAM, but it won't have a GPU, which will basically really speed up your model training, which especially for neural networks. So the way you want to change this is you go to Runtime, change runtime type, and then you want to select GPU here. So note that you can also click TPU. Don't click TPU unless you know what you're doing, because you do have to do certain things to load up a TPU, but you could technically train on a TPU here. I think the notebook that like from last week, Nadine's question, and we had like a thread going on, I shared like a little notebook in there from Kaggle. They actually use a TPU. So you could actually run this with a TPU on here. So put GPU here. I'll click save. And now depending if it was already there, you'd see it reallocate. Okay, and you'd see this pop up here. But you see we're connected and we can actually run our stuff here. So it's really nice. You can actually run commands on here. So remember in Jupyter Notebook, you can actually do exclamation point and then like a terminal command. So in this, for example, I can actually do a pip install. So if there's certain like libraries that aren't installed on here, you can actually run this directly on here. It's just letting me know, hey, this is not by Google. This is from GitHub. Are you sure you want to do this? And I say yes, because I am me and I trust me sometimes. And you can see here, in this case, it looks like requirement already installed. So that means we already installed our like these libraries on here, which is because I already use this. It's probably remembering that runtime. But if you didn't have these libraries, or if you're like, oh, library not found, you could install it. What is nice is that most of the libraries that you are probably familiar with, like NumPy, scikit-learn, Keras, TensorFlow, those are already installed. And I think even PyTorch now is installed on here too. So there's a bunch of libraries that they kind of already have it pre-installed because people use it a lot. But if you need to, you could always install it this way. Okay, and then we can actually just run our stuff like normal. So you can see here, in this case, I have like my libraries importing it. This guy right here is kind of a special thing because one issue here is like you likely, if you're training your neural network, you probably need data, right? So the thing is like, how do we get the data on here? So again, remember, think of this as like another computer on the cloud, right? So like somewhere in the internet, you're connecting it through here. But the thing is like, it doesn't have access necessarily to your files on your computer, right? So the way we can do this is a few ways. Did I talk about this last time? Give me a thumbs up if I talked about connecting files in here. Not really? Okay, good. All right, I've repeated this a few times in the past like week, so that's why I'm kind of like fuzzy a little bit, like exactly what's here. So the way you get to the files, you'll see here there's 3 different little icons here. This is actually the table of contents, so you can actually like quickly jump around to different sections. So if you have your different headers and stuff like that that you're supposed to, you can quickly navigate through it. You also have this guy, which I actually don't use too often, but you can actually go through your snippets and stuff like this, play around with it. I won't go over it today. For the record, I do know people who like use this, like you can find specific snippets and actually insert them in here, but we're not gonna do that. Okay. This is the real part, is the files, and you can see the little folder icon. And you see this is actually what's available for you. So if I actually go enter a new, like I'm using like a terminal command, if I actually do ls, oops, there we go, run this part, you can actually see, hey, sample data. In fact, I can actually navigate into sample data into here. So you can see here, it's like, hey, that's actually like my folder right here. It takes a second because it's connecting. But you can see here, it's like, oh, I'm actually able to navigate through here. In fact, I could do something like, I can create a new file, like touch new file. And you'll see here, it actually creates a new file. Now you notice like, hey, it's not there. Oh, there it goes, actually refresh. But if it didn't show up, you could actually press this refresh button. Okay, so this is kind of like how you can interact with like what's on here. Now, the thing is like, I have data that I want to put on here, right? So there's a couple ways you can do it. One is that we can actually click this button here, which will upload your files. So you can actually upload from your computer to here. Now, that's probably fine if you're doing a one-time thing, or if it's relatively small, you can just upload it, you know, and all that stuff. The only issue is that when your runtime, when basically this notebook disconnects from the other computer in the cloud, you're gonna have to refresh, or it's gonna refresh your data, what's it called? All your files in here. So you'll have to re-upload it every time you connect to it. So think about like you train on this, you know, go get lunch, and then you have to reconnect again, you have to upload those files. So if you have like something that gigabytes large, it's gonna take a long time, you have to upload it every single time, kind of pain in the butt, right? So not ideal. So that's one option that you can do. The other option is actually mounting your Google Drive. So you actually see here, this is kind of new with Colab, this is kind of fun. If you click this button right here, it'll actually import, put the code right here for you to actually connect your Google Drive. So your account, in this case, this is my account right here, is that my account is, my Google Drive account is here, and I can actually put your data in there and everything like that. This will actually connect it. So now basically this is specific for Google Colab. If I run this now, it'll say, hey, you go ahead and connect. It'll give you like a URL, you click on this URL, it'll give you a code, you enter this code right here, and then you can actually navigate and you actually can check out all of the stuff in your drive, which is pretty useful because then that means that instead of having to upload your files every single time the runtime happens, you can instead upload it once to your Google Drive, access that, and play around with it from there. The only thing about this that's kind of the part that's like, okay, this kind of stinks, is that if you want to share this notebook with someone else, they don't have access to your Google Drive. So it means that they won't have access to that data. So I would say this might be useful if you have that data in here, but definitely put at least instructions, just like you would do before, because you don't want to load it into GitHub, your GitHub repo. Put instructions on how to get this data. Okay, so that would be the very least, and say, okay, this is specific for Google Colab. Also note if you download this notebook and run it on your own machine, this will give you an error because your computer says, I don't know what this from Google Colab thing is. It's not installed, and that's because it's specific to Colab. Okay, but this is the other option to upload data into it. Okay, everyone follow me so far? Cool. All right. Now, just before I go into the third way, which is what this is right here, I mentioned about downloading your notebook. You can just do file, download.ipnb, and that will download your notebook, and then you can do stuff. So typically my workflow looks like I code onto my Jupyter notebook, make my notebook there, and then I'll upload, or I use like GitHub, it's like link, but you can upload your notebook on here, do my training, and then download my results, right? So like I'll have all my training, including my graphs and stuff like that from the model training, right? And I'll download that and then upload it to GitHub. I will say there's technically a way you can actually save it directly in GitHub. I don't do that too much, but if you want to, you can play around with it. Okay. So the third part of actually getting your data in here, and this is my preference, is that I actually try to download the data directly onto wherever the person's running the notebook. So what's kind of nice about this is that I can share this notebook and I don't have to worry about someone else trying to find the data. I can literally say, hey, run this notebook and don't worry about the data because basically this will get the data for you. So in this case, this is really useful because this is an S3 bucket. You guys learned about S3 buckets, right? With the section 43, yeah. So S3 buckets, right? Basically think of it just like a dump. It's just you dump everything to that bucket, right? So you can do whatever. And so usually a lot of times data will be actually in these S3 buckets. So in this case, there's actually the zip file right here. And actually have this file right here and I can download this. And so what's nice is that these are some extra libraries like OS and IO. Basically, those are things to interact. One is the OS, basically to interact with like the file system on the computer. The IO basically is a little bit so I can read the zip files and stuff like this. And then URL lib requests, you guys have seen this before. Basically, it's just using like so you can interact with the URL when I actually download stuff. And then zip file, obviously, apart from zip file. Note that these are basically all kind of installed already on here, so I don't have to like worry too much about like installing and stuff like this. So just kind of, would you guys like me to kind of walk you through what's going on in this like little bit of code? Or feeling pretty self-explanatory? Give me a thumbs up if you want me to explain. No, feel pretty good. Okay, you guys are on top of it. All right, so good. This basically, if I run this now, if I go on here, you actually will see, it takes a second, but it'll actually populate over here and it gives me the nice pathways and stuff. In this case, they're pickle files, so I can just have it downloaded in here. And eventually I'll get there. There it goes. So you can see all it's there. And I'm like, cool. I don't have to worry about it. I can just run from here, right? So from there, I can do my opening stuff, do all my stuff. I'm not going to focus too much on that since you guys kind of get the idea. I don't know if you guys can hear my dogs in the background barking. I think the mail person came by and they're like freaking out. All right, so anyway, so this is kind of like, all right, let me show you guys what this project might look like. So pretend on this scenario, I have these, this data set that is a bunch of traffic signs. And basically my goal is to take these images of traffic signs and see, can I classify what traffic sign is? So think like a stop sign, do not enter sign, that kind of thing, right? And so I'm just basically taking this data set that's already been provided for me. It's already been pre-processed, so which is super nice, which is why I'm kind of showing it from this way. But basically I'm doing some quick analysis of this and hey, let me just tell me, say how many objects or how many images there are. There's only 34,800 images for training. There's a 12,600 for testing. And then you can see the image shape is a 32 by 32. And this 3 right here, that 3, if you remember for images, is representing, you know, each channel, right? So in this case, it's probably red, green, blue. Sometimes you can get 4 channels. No, that just means I think alpha and stuff like this. If I had 1 channel, that means grayscale, right? Or in general, I should say, it means grayscale. Okay? And you can see number of classes in this case is 43. So 43 different classes. So a little bit more than like the image recognition that you guys have, which is binary, 2 different examples. Okay. So this is kind of like idea of like how you'd want to first initially explore your data to say, hey, what's in here? Okay. Next, I actually want to check out some stuff. So in this case, I'm going to actually do some visualizations of my data. So before I go into this, like, what would I want to like visualize? here, I'll show you guys first like the set of images, right? So this is like, I just made this little function here to plot random sample of images. So it's going to take X and Y being the labels, right? And basically it's just saying, hey, plot out some random pictures or images for each label. So you can see the different labels. But before I go further, right? So this is me just looking at the data. And I think this is actually a really important part that I think sometimes people easily forget instead of just going right into the modeling. If you look at this really quickly, like you guys tell me right now, what do you guys see from just looking at this set of data? Like what can you tell me about this data set, or what stands out to you guys?
Red.
Red, good. No, that's good. Yeah, you see a lot of red, right? So, and in fact, if I scroll down a little bit, it's not until like this label right here, we actually see something that's like clearly not red, right? But you can see most of the signs are in fact red. So we have to think about this, like, okay, you know, that might mean that, you know, for example, it being blue, there's only a certain number of classes here. If there's no red, it's likely maybe either the blue or in this like, you know, white kind of gray stuff. But most of these signs are going to have red in it. Anything else that we noticed from just like looking at these random samples?
They're mostly triangles or circles. You know.
Good, right? So there's definitely some shapes in here, right? Like you can definitely think of like, I like to think of it when you're looking at this problem before you do your convolution is to think, what kind of things would you as a person use to identify these like, you know, signs? It's like, oh, is it a circle? Is it a triangle? Is there red in it? Is it blue in it? Like those are the kind of like really basic stuff. Like if you're trying to build this from scratch without using convolution, right? Another thing I noticed, I don't know if anyone caught this on, is look at the brightness of these pictures. The brightness definitely varies. Like some of these signs are like really bright and everything, and others are much darker, right? So that's going to be a factor too. So in this case, it looks like, you know, I might want to check out and say, hey, you know, maybe some of these signs for whatever reason tend to be behind other signs, or, you know, whatever reason, like maybe the data was collected, for example, like maybe these tend to be in the darker part. I might want to do data augmentation to make sure I include in my, you know, both validation, but also like my actual training, say, hey, make sure I vary the brightness in here. So these are kind of things like just by looking at some random, like eight images for each label, I'm able to already tell a lot about this data set. Makes sense? Cool. So, and you can see a little bit, like I have a little bit of a, like a little markdown here and talking about like what I see here. And that's kind of the thing I want you guys to do too. So when you guys do a little visualization, you guys should be talking about right underneath it saying, hey, like, this is what I noticed. This is what I want to proceed with, okay? And I said basically the same things like, hey, there's mostly red, white, and blue. So really like the main colors that really stick out to me. And of course, like circle and triangle, right? Cool. And then I think I mentioned that some of these signs look very similar to each other, especially like the blue signs here. Like I think a couple of them are literally like just like rotations and stuff like this. So I probably would be really careful about data augmentation and using rotations, right? I wouldn't want to do a flip because maybe this sign, or I'm trying to think of, oh here, yeah, these two signs are literally flips of each other. So if I flip them, that's not going to do me very much good, right? And like, it's going to get confused in these 30, 30, 34. Okay, cool. Everyone follow me? Seeing nods. Seems reasonable. Cool. So this is where, like, again, like exploration, right? We're kind of going through it. Next thing, let me, before I go into more stuff. So exploring the data set, like what kind of things would we likely want to check out about our data set before we go into modeling for this particular data set? Anyone got guesses?
The distribution of the different classes.
Mm-hmm. Right. There's 43 different classes. We want to make sure it's like, hey, are they all stop signs and the rest are like it's only a couple of the other labels? That's pretty important to know, right? We need to see what class imbalance there is. What else can we maybe explore a little bit? But definitely that's a good first one. Like pretty much any machine learning model you should look at. I mean, this is maybe like as you get like more into like trying this kind of stuff, you kind of see like, okay, what things might actually be an issue. One that kind of stands out to me is like, hey, like how bright are these pictures? Like, do they tend to be darker? Do they tend to be brighter? Like, I'd like to know, right? So like that way I can kind of figure out, it's like, hey, are these actually like a lot in shadow and stuff like that? Do I need to consider those kind of things? Other things I kind of end up considering is like, you know, how much, this is kind of subtle, and this is where like maybe this is more about like experience a little bit, is that I might look at like saying, hey, what's the average brightness in certain channels? So remember we have red, green, blue channels, right? And so I would expect, for example, like in this in this image right here, the blue channel to be like the highest brightness in like overall like red and green, right? Because most of it's blue. Same thing for like, the stop sign up here. I'd expect most of it to be in red, right? So like, it's like, oh, I might want to explore that. And I can kind of think about, like maybe I could actually find like I'd actually build an algorithm without using convolution. It's like, hey, if it's like a red sign, maybe it's one of these signs. Or like, hey, it's mostly blue. Like that might be something to look into. So this is the kind of thing of like when you're thinking about a baseline model, what is the simplest solution before you just dive into like deep learning or something like that? That's the kind of process you should think about. And it'll also help you with convolutions or anything deep learning to help debug to say, where is it falling apart? Where is it messing up at? Okay. So just like Alvaro said, I do a distribution of classes. You can see here is that there are definitely some classes that are much more common than other ones. I think I show like the minimum. Yeah, there's some image labels. There are 11 images with less than 300 images in the training set. And then there's 3 classes that have over like almost 2,000 images. And those are like those top ones up here. So you can see a little bit of the distribution of what those classes are. I'm actually going to skip any like, class imbalance, but you could definitely like look into that, especially if you look in our confusion matrix. If we're seeing things like really mess up on these small numbers, you definitely would say, hey, like it's probably like we need to actually generate some extra images in here or deal with this class imbalance. Do we always have to do like how do I say this? Do we always have to make sure our classes are exactly equal? Yeah, shake some heads, right? And hopefully like the way I asked that to kind of implies a little bit. Is it ideal to have them equal? 100%, right? Because if they're equal, the machine learning algorithm cannot rely on the fact that it's just more common. But in some cases, you can actually have class imbalance because if these like less frequent images are very significantly different from the rest of the images, then it's going to, there's a chance at least that the machine learning algorithm will find those unique differences in those like small classes. The problem is when basically this class right here, which is very few of them, is very similar to like this class over here. Then the problem is like, well, out of pure numbers, it's just going to guess this class, right? So this is the kind of thing that you have to consider when you're actually like looking at like what do we have to do with class imbalance. Okay, makes sense? Cool. And note that I'm talking about images here, but this applies for like any like class and stuff like that. Okay, and then I talk about brightness by image. So I kind of do some stuff where I'm actually like looking at the brightness overall. I won't go through the whole stuff. You can check this out. I'll make sure to share it with you guys to like look through the code and stuff like this. Note that basically I'm building up a little bit of a pipeline so I can actually pull up this data into a data frame. And my goal is actually going to train a machine learning algorithm just off those features themselves. In this case, I looked at for the pixel brightness, the average, the variance, right? Basically the standard deviation and the median. And I do that for all the channels combined, so think like grayscale. And I do it for channel 0, channel 1, channel 2. So red, green, blue channels. And what I want to see is like, hey, if I go ahead and actually pull up these features essentially for each image and stuff like this. So each row here is in this data frame is going to be a separate image. And now I have, what's this, 12 features right here. So those features, can I actually do a decent job of predicting without doing any convolution, no deep learning and stuff like this? Because if it's really easy for me to do this, if I get like an 80% accuracy, then I know what to expect from my convolutions. Like I should at least get that, percent and probably, higher from there. If I find this to be really difficult to do, because like I think it's pretty easy, but like if I find out like, oh, it's really bad, then there's a lot of improvement from convolution, then maybe I need to look at more complex stuff. So for example, if I'm getting something like, the real baseline model is just randomly picking, right? And I would expect like, oh, like, 1 out of 43 or 1 out of 43, whatever that percentage is, right? Anyway, if I'm finding that that's my accuracy, like that's what I need to beat at the very least, right? Very, very baseline. But if I can beat this, I can probably be pretty confident I have a much better result because this is like took me no time. Like there's only 12 features in here. So this will take no time to train with like a random forest. Does that make sense to people? Cool. Any questions at all? Like what I'm doing or why I'm doing this? Cool. All right. So yeah. Anyway, I think this is important. Oh yeah, go ahead.
So basically what you're saying is we're creating, sort of creating a new data set, and we're going to use, and then we would use a machine learning classifier like a random forest or one of the boosting classifiers, whatever, and run it against that, and that would probably be a good baseline right there, right?
Right. And the
But
idea here is we're doing something relatively simple that we can like iterate really quickly and not have a huge amount of data. Like I can take the average brightness pretty quickly, the variance of the pixels brightness pretty quickly as well. Yeah. And we're basically just saying, hey, how well does this do? Because again, this puts in perspective of how difficult this problem actually is and how much benefit we can do from using something like deep learning. Think of it this way. If you're talking to, let's say like your business, and you say, hey, I can like, we could do deep learning and like maybe get like a better percentage, but like I can get like 80% accuracy with like a really simple model and we don't have to pay for any like GPU time. People are like, yes, let's do that. Like that seems really great. Or maybe they say, you know what, that 10% is going to be really useful for us. And this is where, again, tying it back to that business problem, saying, why is this going to be useful and how is it going to be used? Okay, makes sense. Cool. All right. Yeah, so just basically, you guys know how to do a machine learning algorithm now, like something like tabular data. Essentially, that's what we have. We do that, and I go through just a really basic random forest. I don't even try to iterate off of different stuff. And you can see the accuracy, hey, not bad. Even with not weighted, right? 13%. Like, hey, that's not too bad for accuracy. It's not great, right? It's definitely not going to be put in any self-driving car anytime soon. 13% accuracy is probably not great for like running through stop signs and stuff. But you can get an idea at least like how difficult this problem can be. Okay. Sound pretty good. And then I put a little confusion matrix here. And you can see here what's kind of interesting is that this label, I know it's really small and the font's really small, but you can guess right here is probably all our blue signs. And you can see that's where it's the most confusion is coming up, right? So you can kind of quickly look and say like where it's messing up. It's like, yeah, we kind of expect it to mess up on this blue area because probably they're all very similarly blue. So you probably have very similar features in that case. Okay. Sound pretty good? All right, any questions? All right, cool. So then it comes like, all right, that's cool, Victor. like you may have been for us, but that's not the point of this project, right? It's to do some convolutions and deep learning. So this is where we say, okay, like now that we have kind of an idea of what this model can do, like really basic model, like what can we do with convolutions and like deep learning? So one thing I did want to put out is that this has actually happened to me when I was kind of playing around with this data. I actually didn't one-hot encode it at first. And you guys know how one-hot encoding works. I didn't one-hot code the labels, which is really interesting because it turns out is that the way this labeling system is already put together is that, for example, it's most obvious, I think in this blue, 33 to 40 are actually very similar to each other, right? And so what's interesting is that like, let's say the model is really bad at predicting or it gets lazy and doesn't want to really predict. It might look say, hey, it's a blue sign, randomly pick between 30 and 40. And what's nice is that it's easy for the machine learning model to actually build up a function that has, put out 30 to 40, right? And choose a number between there. And it's going to get relatively close. So like, let's say the label is actually 37. It'll probably get within around this area just because the numbers are close together. So what's interesting is that I actually kind of show a little bit is that if you don't one-hot encode, let's see if I show it here. If I don't actually one-hot encode, which I kind of skipped over this part, Oh, this is it. I'm trying to think where I put this in here. Maybe it is in here. Sorry, I'm kind of skipping around a little bit. Oh, there it is. Model without encoding. So I actually do like a neural network convolution. We'll talk about what those look like, but I actually try to fit it without one-hot encoding just on the validation set. It actually does over like, I think it's like 15 epochs after early stopping. It's like a 92% accuracy on the validation, which you might say, oh, that's pretty good. But we'll later find out it's like, oh, that actually like, it's actually doing a lot better than you would expect. And it seems to be just from the labels themselves. So this kind of emphasizes the points like making sure that how you put your labels on are actually a really important aspect of your model training itself. And so one solution would be mixing up the labels, but probably the better solution is just one-hot encoding because then there's no association with the number in the label itself saying, oh, 33 and 34 are close together, where instead we have like a bunch of, a long vector of 43 and just having zeros and ones, right? Or I should say a bunch of zeros and 1, 1. Okay, makes sense like what I'm talking about like when I say labels like that? Cool. It's a subtle thing and it's easy to miss. But this is where, for example, you might actually do one thing and then it's like, oh, let me go ahead and go back and change it. And like say, oh, we do have to one-hot encode because I found this issue later on. And you can even mention that in your like, let's say you went down that tangent and you find out like, oh, one-hot encoding, I have to do one-hot encoding. You can then go back into your notebook and say, okay, like we're going to one hot encode because there's this issue. And you could talk a little bit about saying you did run into this issue, or you could just say, oh, we'd run into this issue, which is like actually because you did run into that issue. So that's the kind of way you can kind of structure your notebook and as you're going through it. Make sense? Cool. All right. So let's go through this. Just pre-processing it, normalizing the image data. So that way, remember, neural networks need to have small numbers, right? So our pixels go from 0 to 255. So we need small numbers because neural networks like small numbers. They're scared of big numbers. There's a whole bunch of reasons for that, but we don't have to go into detail. And in this case, I just literally defined to say, hey, subtract 128, divide by 128, close enough. Like you could technically do a different normalization. You could even put a batch normalization layer in there to actually normalize everything. But this was a really quick and dirty way to do it, and it seems to work fine. The main part is just get small numbers. And then I actually have my TensorFlow here. So this is where having a GPU is going to be important. So if you do import Keras, so you don't do like from TensorFlow, and you just import Keras and use Keras from there, one of the issues is that Keras will, it's kind of like an API, meaning that it's kind of the layer on top. It allows you to like, interact with it. The thing is that Keras actually allows for a backend. And so TensorFlow can actually be working as like the backend, and basically it's going to do all the heavy lifting, but you have to specify that. So the easy way to specify saying, hey, use TensorFlow, which can use the GPU, is basically just importing TensorFlow or Keras from TensorFlow, because there's a Keras API built into TensorFlow itself. So this is a classic problem where most people will just put like import Keras like this, and then they'll use Keras. It's like, man, my model's running really slow. It's like, it's probably because you didn't have a backend, which is probably TensorFlow. So note that that's why I'm having this. And this is usually a really easy way to just import Keras, and you can just use Keras like normal. And then if you want to change the backend, you can just import Keras from a different new library. So cool. Does that make sense to people? Yeah. This is a nice trick right here, just so you know, and you'll see this a lot. Okay, and so let's see here. In this case, I actually took this from, let's see here, the hands-on machine learning book that I mentioned about, that long title. Yeah, this actually came from here. That's actually some of the stuff is structured off of this. But this is actually a really cool thing, is that they basically created like, it's like, well, I want to use the same convolutional neural net or convolutional layer every single time. So we actually are creating a partial, using the partial method to basically say, hey, this is the original like method we have. So we'd have keras.layers, convid2d, and then we'd put in the parameters in here. And then the rest of these are just all the parameters that would go into this method right here. And that basically builds up a new method called default convid2d, and with these particular parameters. So this is really useful because, for example, you can see how long this is like the normal way, how long this could really be. It's a super long thing and using the same thing over and over and over again, where it might be a little bit easier. For example, if I do like default, like I use, oh, that's relatively easy for me to like change. All I have to change is filters, but these will be the initial parameters. Okay, does that make sense? Like how that change happens? Yeah, cool. It's just a nice kind of convenient thing that Python has. And so the rest of this now is like, all right, let's actually build some model architectures. So in this case, I actually built, like, you don't have to do this necessarily, but I like to kind of confine things into nice methods where I can like basically just call them and like, no, I can just change things in this method and then just use the same methods over and over again. So in this case, I have this model architecture here, which I call this basic CNN, and I just put a little label here so I know like what it's doing. And I put a little comment here because I found it's about 94, 95% accuracy. But you can see here, this is my Keras right here. And remember, Keras is actually from TensorFlow, so it's going to use that backend. I'm using model sequential because we're using a sequential model, CNN, right? And then we're basically taking our different, just building it up, right? So you can see here is that in this case, I actually build up a convolution layer, in this case, 64 filters, okay? A kernel size of 3, okay? Activation ReLU, I mentioned about ReLU before, keeping padding the same, so that way it can have a nice padding on this outside. And then notice I also put this kernel initializer in normal. Now, this is kind of a subtle thing, like, well, why did you do this part? Turns out this actually works well for convolutional neural nets with this initializer. Normally, the initializer is initialized with a normal distribution. This is a slightly variation on that, and it turns out it just works better. So that's why I put it in here. But if you didn't come across this, I wouldn't stress out too much, being like, oh, it's not going to like amazingly do better results. It's just going to converge quicker. So that's why I have this in here. Okay. And then you can see my normalization. So basically, I like to put normalizations here because it does help basically speed up training in each epoch. It does take some time for it to actually do the back propagation. It does take some time for this to happen, but it usually evens out. So it's one of those things where, like, I'd say normally it's perfectly fine just to use this. There are a little bit of controversy, a little bit of research to say that it's not really necessary, but it's worth it. Like, people have been using this for quite some time, and it seems to be fine. But anyway, I have my convolution, my batch normalization. I now have a new convolution layer, which is 32 filters, right? Same kernel size, then another batch normalization, convolution with 32, and then a max pooling. So the reason why I have this max pooling here versus, like, right here is that I'm doing basically 2 filterings in a row like this, and which will technically add more complexity. And so I want to reduce that complexity. And so I add a max pooling right here of basically a 2x2 grid. So it does reduce that dimensionality. It does reduce that complexity in there. And basically it keeps it from overfitting a little bit. Okay. Makes sense? Like, kind of what the structure looks like. Yeah. Cool.
Why not max pooling at each layer, at each convolution layer?
You could do that. It might just reduce too much. So there might be too much complexity loss, which means you'll start getting underfitting instead of overfitting, and kind of like hint a little bit of like what happens. This actual model actually tends to underfit just a little bit. So there's actually room for improvement. So if I added another max pooling in here, it probably would underfit even worse because it's just losing information. So that's kind of like a little quick cheat a little bit. So if you're having you'll see this commonly, 2 convolution layers in a row and then a max pooling. So again, like, how do you know this works? Pretty much because other people have done it. Like, that's kind of like how that research goes through. So this is where you should look at what other people have done and see what results they've had. So I have this convolutional kind of like block right here. So you could even, if you wanted to, you could define this whole block as like a separate function, but we just have this together. I add a dropout to basically reduce that complexity. So that's kind of similar to max pooling. So note that I don't have dropout each one, but I have it afterwards. No, I think I mentioned this before. Dropout with like a 40% usually does pretty decently. 40 to 50% for convolutions does pretty well. With a neural network, you probably want to drop that closer to like 20%, which I'm looking at this right now. Actually looks like I don't use 20%, I use 40%, which might be why it was underfitting a lot. Anyway, do this dropout, do a new convolution, and note that it's 64 filters. So in general, as you're building up your convolutional neural net, you kind of want more and more complexity from it, right? So think of it like the lower levels when you're doing those filters. It's going to find very, very simple patterns, right? So think of like this is even more complicated than the first initial layer, but like think of like it's finding little spots, little lines and stuff like this, nothing too advanced. And then as we get into deeper and deeper layers, for example, like we might eventually find things like, looking for like circles and triangles and stuff like this in the filters. So more complex patterns and stuff. And so we want to allow for more variation in those complex patterns. So we usually increase the number of filters. So that's increasing the complexity. So essentially what we're doing here essentially is going from very relatively simple to more complex, which is why it's represented with these higher number of filters. Make sense? Cool. And again, you can say, how do you know this? Like, oh, research, right? This is why it's always useful to like see what other people have been doing in the academia and seeing what works. Okay. All right. And then at the end here, we are done with our convolution in this case, and we went straight to our fully connected neural net, or our dense net, or our multiple perceptron network, right? Whatever you want to call it, all the same thing. In this case, I added a dropout right here, which is because of this part right here. I skipped over max pooling. I don't really know why I did that. I think I probably would have had a max pooling in here. I probably just didn't put it in there. I was just kind of making stuff in really quickly. And then you can see here is my actual
You beat me to my question.
Uh-huh.
You beat me to my question. I was going to ask you why there wasn't a max pool layer there.
Yeah, Fast Victor was just doing something really quickly. Probably he messes up all the time. I like to blame him. So anyway, we have we probably should have a max pooling here. We can do our dropout, and then we have our fully connected here. I start with 128, 64. So we're kind of reducing now the complexity, right? The idea here is that we're trying to get to the point where we have most of the features here, and we'll just kind of reduce it down to find this. You might see more hidden layers in this fully connected, but remember, all you're doing basically is learning off of whatever this output here is, learning off all of those feature sets now. And now it's saying, okay, taking those features, let's train off of this fully connected. Okay, and you can see units 43 because it's going to be outputting to 43 different classes. Okay. Sound pretty cool? Yeah. Any questions at all about like how I structured that, besides Fast Victor messing up and earning enough in his convolution architecture? Yeah. Okay, cool. And so I won't go through the whole details like I did for the other one, but you can see, for example, a little bit more complex. I have starting off at 32, 32, and then I should go max pooling. Yep, good. Max pooling, I do a dropout, then 64, 64, max pooling, dropout, and then our final guy right here, which again, I think for the record, I don't know why I use 40%. I actually wonder now if I actually change this to 20%, how well it would do. Usually you're fully connected, you do something around 20% to 30% for dropout to reduce the complexity. The reason why, again, is because dropout tends to just, the convolutions tend to have a lot of information, so we want to drop out some of that more information in there, and it just turns out it does better here because there's a lot of complex information, where the fully connected doesn't have as much densely connected information. Ironically saying dense, but anyway. So, and then you can see this last layer here, I just, for fun, added a new convolution. That's really the only difference. Okay, and so now I have these three different model architectures. You can compile it, right? So we already know how to compile, for example, model.compile. So if I were to pass in the model, I can compile with this loss function. In this case, I'm just making it more general so I can come back to it later. Categorical cross entropy, since I have multiple categories, right? So this is pretty typical for your loss function here. But you could change it to something else if you felt that was something more useful for whatever reason. Note that I use an optimizer natom. I like to use Nesterov atom optimizer. Usually that does pretty well with the momentum Nesterov, right? So you'll see me use this commonly. Preferably don't use SGD. Stochastic gradient descent doesn't tend to do super well on these kind of problems. It can still get decent results. You'll still see people use it every once in a while, but usually in optimizers, usually what you'll see is that atom tends to do very well. Note that atom doesn't do well for everything, which is why I put Nesterov in here. Usually Nesterov kind of helps it along, if it does have issues, but it's just really dependent on the data set. And then you can see I actually have some metrics in here, accuracy, so the accuracy will get reported too. Okay. And so I actually returned this model because I made it into a method. So we can return this stuff. And then I can say, all right, cool. That's the idea of how I would compile it. Let's go ahead and actually train and test this, right? So I built a little method here called eval model. So note that I'm taking the model history. So when we actually do the model.fit, we actually can keep the history. You'll see it right here, history equals model, right? So we can actually keep the history and we can actually plot out like how it did over time. So that's why I actually pass this in here. So I can actually plot this out. So usually you'll see, like, for example, history equals model fit. And to actually call those values out of here, you will do model history, like dot history, right? And pull out the loss, the validation loss. In this case, this is the training loss, is the validation loss. And then I can do like little plots in it and stuff like this. Okay, cool. Makes sense so far? Like pulling this history out? Okay, cool. See nods. So this one right here, I will use like those methods I do in a second. But I'm just showing a little bit like what this looks like if you weren't to use that method. So in this case, I have this model equals compile model, which is what I had before. So I have this compiled model, which again, just this guy right here pretty much, right? And then I'm just gonna do a model.fit. So note that I'm normalizing this image data. So remember that's 128 divided by, or minus 128 divided by 128, so I get small values. My Y train, which is one, this is not one hot encoded, so eventually I would one hot encode this. Epochs, I have 16. Eventually you'll see me put it up to like 100, 150, and it's just gonna early stop. So generally you want it to go, if you put early stopping in there, you want it to go longer than your early stopping. That way you know that you actually reached something that's like decent to where you stopped it at. And then I pass in my validation data. You could technically do a split here, but I prefer to actually have the validation data already predefined. That way I can be consistent every time I test my model and fit it, okay? And then note this verbose equals 0. That's because I just didn't want a bunch of junk in here. But if you put verbose 1, which is the default, it'll do that little line where it's training and you'd see each line go through. Okay, cool. Pretty simple, right? And then you can see the evaluation model. Basically, it's doing this guy where it's taking the model history, right, which we got the history from the model.fit. And we're actually plotting out then the actual losses and accuracies for the training and the validation set. So note that basically everything on the x-axis is an epoch, right? An epoch basically thinks like that whole iteration of all the batches. And you can see here it goes 0 to 16 because there was no early stopping. And you can see is that in general, we see the validation loss right here going pretty small. And in fact, and note that it's kind of like, you're like, why is it underneath the training? Which might kind of give you a little like, that's kind of weird. Part of the reason why is because it's off-centered by 1, because you get the validation loss at the end of your training. So it's basically already trained on here. So that's why you might see something like your validation loss be under, which in general you really shouldn't have. But that's why you might actually see this. Oh, disconnected me because I took too long talking. That's fine. We're not going to really run things. But you can see here basically it's getting smaller and smaller, and you can see it's actually following the training loss right here. I know I'm close on time. Are you guys cool if I go an extra like 10 minutes? All right, cool. I think this is useful, so that's why I'm willing to go a little bit extra. So you can see the loss getting smaller and smaller for both the training and validation. Looking at this graph right here, what would you guys say? Is this underfitting, overfitting? What should we do next? Any suggestions, and why do you say that? So first, are we overfitting or underfitting?
Looks like underfitting.
Yeah, right. There's still room for improvement here. Like basically, our overfitting would be as if we would get the validation loss getting farther away from the training loss, right? So our training loss essentially getting worse, or basically that gap is getting bigger. So in this case, it looks like there's still quite a room for improvement. So based off this, you would say, oh, we probably should keep it going. We need a more complex model. And more complex model might just mean more epochs, more time for training. But it could also mean actually having a more complicated model architecture and stuff like that. Okay, cool. And again, this is actually kind of like, it's like, oh, this is actually not the best thing because we didn't want hot encode, which is not obvious from here. I was saying like, oh, why it did well? Because again, it's doing well because the labels are in certain order. So if you wanted to see this again, the smart thing to do is show like, oh, it's actually the labels that are kind of allowing this thing, is to actually mix up the labels, the numbering system, and then you would probably see that this would not do as well as it did before. Okay. So, okay, I think you guys at least see the model, like how this works. I can kind of quickly go through a little bit of like this training, like what this looks like. I'm going to iterate over a bunch of models, and then we can actually see like using these checkpoints, for example, like early stopping and saving your best model. You guys want me to go over that, right? I'm guessing. Yeah. I see some nods, so good. All right, so this is where, again, like this is like the really simple stuff, but you guys aren't simple. You guys got better stuff, right? You guys can do all these really cool, fancy things. So model checkpoints. If you're not sure what I'm talking about, look up Keras model checkpoints. I think I have it in the notebook that I talked about before. It's really useful to basically do certain things. So as you're training through here, one of the issues is that if you start overfitting, basically that means that you went, essentially too complex, right? So one thing you might see, which is pretty typical, is that you have, like, say, instead of 16 epochs, you go for like 2,000 epochs or something ridiculous, right? And the problem is that you'll probably eventually see your validation loss get worse and worse and worse and worse and worse. And then it stops here and you're like, oh, shoot, like I should have stopped back at like 16 and I went all the way to like 100 over here. And you're like, oh man, like I had, and then I think the curriculum technically says like, oh, you can then, now you know it's supposed to be 15 epochs. And you're like, oh, I got to retrain this whole thing over again. Like that's such a pain. So the smarter thing to do is like, let's just instead, like, could we like go back to here and like just use this model, like when it was here, like go back in time. And that's what early stopping can do, or saving your best, or model checkpoints. Basically you can make checkpoints where you can do it like every few epochs or only when the model gets better. Basically making these checkpoints so as the model progresses, you can actually go back to that specific epoch time. So sometimes you can save every single epoch, which I wouldn't recommend, especially if you're doing many, many epochs. But you could, for example, go back to like every 5 epochs and go to that specific model where like, hey, I already got the answer. Like, let's just go back to that answer over here. That's what checkpoints are basically doing. Make sense?
Yeah, so you can run both early stopping and checkpoints, right?
Mm-hmm. That's right. So I'll show you what that looks like too. You can do a list of different model checkpoints that you want. And what's really cool, if you get really excited about doing this, you can actually define your own model checkpoints using object-oriented programming. You can actually define whatever you want. Like for example, TensorFlow, or I should say technically Keras, is that you can use basically the object-oriented programming to design your own model checkpoints if you want very specific things, to say, oh, now I want this checkpoint for whatever reason. So yeah, and you can have multiple. So let's see what that looks like. So again, I'm just making, I like to make these methods and stuff like this so I can kind of encapsulate everything, and then I like to iterate over it really easily versus like copy and pasting stuff. So in this case, what I'm doing here is basically saying, all right, here's my model string, and I'm going to save this, whatever the model is as it's getting trained, it's going to save in this folder called models, and then actually have a model type. In this case, you can actually see model type is this guy right here. It's what I pass in, but you can put whatever you want here, and that will save it into folders, and then this model string. So in this case, I call it like best model, but it could be like, usually people just say model or something like that, or like results or something. And basically this will save now your model checkpoints in this folder structure with this model string. Now what's really cool about doing this, you can actually add on, because sometimes people will say like model 1, model 2, best model, like they'll save different models and stuff, and they'll have their own naming scheme. And you have to manually do this, and you have to remember like, what was model 5? Was model 5 better? Like I can't remember. What was different about model 5? Don't do that, right? Why give yourself more work? So this kind of gives you more structure at the beginning. Where it's like, oh, this is the model type. In this case, I have like the basic model, CNN, whatever kind of thing. And then you can have that in a folder. And then what's cool is this string right here. You'll notice it kind of looks like a F string with this formatting. And that's because basically by passing in this checkpoint for TensorFlow, well, I should say Keras, is it basically says, hey, for the epoch, just write the epoch right here, epoch, and then it'll say whatever, how many epochs it is. So if it's on the 5th epoch, it'll say 5th epoch right here. In this case, I have just a little formatting string. So if it goes past like, if I were to go like into like the hundreds or thousands or something like this, it would just keep it here. This probably wasn't needed. You could probably just put the epoch here. But it's nice if I have this with this leading 0 here. So you guys know formatting strings. It will not just say epoch 5, and the next one will be epoch 10, if I'm doing every 5 epochs. Problem is like it doesn't order well, because then you'll see like in your data, you'll see like epoch 1, epoch 2, epoch 3, but there'll be epoch 1, epoch 10, epoch 2, epoch 20, right? Like things like that, which is kind of annoying to sort through. This leading 0 allows to go like 005, 00, or 010, 015. So it's a little bit easier to order. So that's why this is not really super important, but I think it's kind of a nice thing to realize, like, oh, I can put this leading 0 in here. And then same with validation loss, I can say how much the validation loss is at that epoch. So in this case, I can quickly look at my file, my checkpoint, and actually see, oh, it was this model, because it's under this model type. It is my best model, just because I just gave it that name. It was on epoch whatever, and it had the validation of loss of this. So I can quickly look at it on my files and know how well it's doing versus having to load it in and see, like, was this the right model? So give yourself, like, work with your past self, right? Or work with your future self. And yeah, I'm getting confused with timing. But anyway, that's what we're doing here. So anyway, that's what this extra stuff is basically doing. And then this is the actual checkpoint, the save best. So you see a TensorFlow.Keras. I could have just done Keras since I imported it. Callbacks.model checkpoint. I actually give the file path, which is this guy right here. And then I'm having the monitor, which I'm monitoring validation loss. So I'm saving the best model based on the validation loss, which is important, right? Because that's really what matters. That's kind of like me doing my little practice test. And then in this case, I'm only saving weights just to save on space, but you could remove this. You could do false if you wanted to. Mode auto, you almost never need to change this mode here unless you have a specific reason for it. Read the documentation if you're curious. And then save best only equals true. So that way I'm only saving the best model versus like every 5 epochs or something like that. I'm only saying, oh, when the model gets better, save that checkpoint. Okay. Any questions on this? I don't think I saw anyone raise their hand or anything. Feel free to interrupt me if you guys have questions. All right. Let's hear. Okay, and this is another checkpoint right here called early stopping. So we talked about early stopping, like what that looks like, right? Basically, it's like as the model gets worse, why spend all that time? Like, like it's like if you pass your destination, like, well, we said we're going to go an extra 20 miles, so we're going to go an extra 20 miles. Like, no, just stop, right? Like, stop training. Like, why do we keep going? We know it's going to start overfitting. So this is what this early stopping checkpoint does. It's basically saying, hey, I'm going to, in this case, I'm monitoring validation accuracy, which I don't really know why I did this. It'd probably be better to do validation loss. I probably just did this for just like showing purposes, right? Say, oh, stop after this validation loss gets worse. The min delta basically saying what counts as like a change in the validation accuracy in this case. In this case, I put like a 0.01% change. So by default, it's actually 0. So that means if there's any change at all, it's going to consider that being better, right? So any like positive change, right? So like if you have validation loss, a smaller number would be better. So any change that's smaller is oh, that would be better. So in this case, you can say, well, I don't know if that's really better if it's only increasing by 0.00001%. So I say, okay, let me have an actual like strict value. It's like, oh, if it doesn't do better by this amount, like that doesn't count as like doing better. Makes sense, right? It's barely inching forward. And then patience equals 8. That just basically says, oh, I'm waiting 8 epochs to go through. So if I say, oh, this is my best model, the next epoch's like, oh, it didn't do very well. The next model, oh, it didn't do very well. The next, next epoch doesn't do very well, right? It has to do that 8 times before it says, all right, you've had 8 tries to try to get this better. Like, sorry about it. Like, you need to go home, right? So that's where this early stopping comes in. Okay. And what's nice, I like putting this here, restore best weights, because why would you, if you early stop, like, let's say 10 epochs or even like 50, I've seen people do 50 epochs for certain models. It's like, why would you go, like, why would you restore the 50th epoch after they're not doing well? Restore the best one, right? So I don't know why anyone wouldn't do this, but it's not the default, so put them there. Anyway, once you have these now checkpoints, they're already made, right? They're kind of these methods that are built in, or I should really say they're objects. And now what I can do that on my compile like I normally did. I have my validation sets, which is, just getting our validation set, and then actually doing the dot fit. And you'll see I have to normalize, by train encoded, epochs, I define how many epochs there are, batch size, we talk about batch size, and then callbacks. This is where you put in your model checkpoints right here. And you can see here in this case, I have save best and then stop after 8, no change, right? So that way I know, oh, early stopping and save the best models. Okay. So just note that if you didn't have, if you don't have just save best, for example, you could just have callbacks equal save best, or you could put save callbacks list save best in there. Okay. Makes sense? Any questions on that? All right, cool. So this is kind of a subtle point now. It's like, all right, we trained the model, right? And you got these checkpoints. And you're like, okay, but now I want to like just load that model checkpoint in here. This is like super useful, especially because if you have now that directory of like your model checkpoints and it's saving every best one, you can say, hey, go ahead and just load up the best checkpoint from that, from my checkpoint or my latest checkpoint, which in early stopping should be my best one, right? And I can just load those specific weights on there for my model. And that way I don't have to like reload it. And what's nice about this is that I know for sure when the model's done, the model's in its best prime spot, right? It's like all trained, it doesn't have any extra gunk that would have happened. I have my best model. And so I have this return and I can actually do that. And that's where this model dot train here, basically I can just train one model at a time. I can evaluate it and look at the pretty pictures. Ooh, right? So you can see here, like it's doing pretty well here, like 93% accuracy on the, what's this, the test, oh, and the test set. So hey, not bad, right? So this is the kind of way you can kind of iterate on it and check this out. Now, if you get really excited, and I'll kind of give this, and this is kind of where I'll stop it for if you guys have any questions. In this case, I just have, because I had the model architecture, and I said get model architectures, get all the keys, iterate over every model type. So I have like 3, 4, 5 different models, and I have this model types, iterate over. It's like, hey, model history, model train. I just have this part right here, and then actually print out this validation. And boom, I just let this go and I can walk away and never have to like worry about that specific part because I know my functions work well and everything like that. And I can just have it train individually and I can actually see how well it does. So in this case, I think I didn't run this part, so it doesn't have this part, which would be actually separating out each part. But this, for example, is my first model, which I think is like the basic model, and then it goes, more complex. And my basic model actually does pretty well. You can see here about 96% accuracy on the validation, and I've actually do the testing set, which for the record, when I did the testing set up here, you should only use that once you're done training your models and actually want to evaluate and compare all the models at once. So you can see here, 93.8% for testing. So not bad, not bad. And you can see here, it does for the new model. This is why I inserted that new bit of string here so you could actually see the difference. And you can see here, this is the new model. This is the more complex one, which looks like it doesn't do that much better. Actually, it does a little bit worse than before. In fact, it starts to overfit, which kind of makes sense. Like you can start seeing it overfitting a little bit because it's more complex, right? So you would expect it to start overfitting, right? And you can see here on the test side, it actually doesn't do that much different. I think it's about the same. So it's like 0.5 or 0.6% different. That's not too bad. And then you have the final one right here, the most complex one, which again, you can definitely see that overfitting here, is that if I let this keep going, it's going to keep going up, right? It's not really training. It's kind of having issues here. So at the end, I have something around like 94% accuracy, which is not bad. But then from the business case, this is where I don't have anything to talk about this. Business case, you'd probably say, hey, like this is how well we did this accuracy. Is this good enough for like self-driving cars? Probably not, right? 94% is probably not a good enough accuracy for determining which signs it are. I also haven't looked at, in this case, the confusion matrix, like, does it mess up on certain signs? So for example, there's this class imbalance? Are there any issues there? What about all those blue signs? Does it know what all those different blue signs are? Or are they just basically just guessing at this point? So this is where a confusion matrix would be the next part of like evaluation. So that was kind of me going through a whole bunch of details about how you might do like this is kind of like a mini project of what you guys have. But hopefully you guys get an idea of like what kind of evaluation stuff, what kind of process that looks like. Any questions? I know we were over time, but do you guys have any questions at all?
Just one thing.
Mhm.
So if we're using a pre-trained model,
Mhm.
and so I just want for anybody who hasn't thought about it is that if you use something like VGG16, which has got a huge output, right? It's got a whole lot of labels, over 1,000 labels, I think, right? And you're
Mhm.
using it for a binary classification to classes. You have to remove that final layer, the output layer, and replace it with a binary layer, right? Only two nodes at the end.
That's right, and that's because it, like exactly what you said, Alvaro. I think it's trained on ImageNet, which is 1,000 different classes. This is true for any model you do. You have to consider what the actual architecture is doing, and also considering what it was trained on, right? And so, in that case, if you have a different output, which you guys do in this case, and probably most cases for transfer learning from like other big models like that, you probably have a different output. You have to basically cut off that last bit of the fully connected section and put in your own fully connected section. So there's a bunch of ways you can do this. I think the curriculum talks a little bit about like with like different transfer learning stuff. We didn't go specifically over this notebook, but it's worth pointing out. Is it deep learning, transfer learning, and then transfer learning here? There's some good like rule of thumb kind of stuff. Is that when you're doing transfer learning, there's kind of like 4 main like sets of like how you would do transfer learning. Basically, if you have a large data set or a small data set, and then if your data was similar or if your data was very different. And that kind of tells you a little bit of like how you structure your, what's it called? How you structure your transfer learning. Do you retrain the whole thing, which probably in this case, I will tell you guys right now, don't retrain all of VGGNet or VGG16 or ResNet or whatever you're going to use. It's going to be really, really slow and you might not get good results because your data is relatively small. So in general, for this project in particular, you probably want to use something like this where you're using basically to at least the weights to kind of shortcut. So you use the pre-trained weights and then train parts of it, or literally run your data through your transfer learned model, right, with the weights frozen, get those bottleneck features, and then train those bottleneck features off, either another CNN or even just a dense network. I will say for this project, definitely focus on like at least trying to build like your own convolution net, play around with that, kind of get an idea like what to expect. And like when you see results like, oh, I was underfitting or overfitting, think about like how you would change that, make an iteration on the model to either reduce complexity or increase complexity, see how well that does. And then if you do have time or, you have like, a little extra, just ambition to do it, transfer learning can give a lot of really great results. So it does take a little bit of work. It's a little bit different from building up your own convolution, but it's definitely worth it because I think this is in general where most people will find the most like bang for your buck. Like if you're in a business, you probably aren't going to try to train your whole network, trying to figure out this one thing. It's usually a little bit easier to just use a transfer learning thing, and usually that gives really good results. So yeah, I don't actually know if that answered a question, Alvaro, or like just kind of like open up.
Well, mine wasn't a question. Mine was
Yeah.
just a reminder to anybody else who's doing this project that when you do it, if you're going to use transfer learning, don't forget that that output layer has got to be very different. And even the last couple of dense layers have to be
Mm-hmm.
different than what than what you have.
Yeah, definitely. I would say what's usually the best kind of strategy for transfer learning is freeze up most as close to the top as possible, and then change like the most like the output, and then go backwards. And the first one basically is like, oh, like your dense network, change that up to make it suitable for your results, like, or for your labels, see how well that performs. And then if you're like, oh, that didn't do very well, then you could start basically unfreezing layers as you work backwards, because most likely those beginning layers are going to find similar patterns, even if your data is very different from the original trained data or training data from that original model. It's likely going to find a lot of similar features and patterns and stuff, and you can use that to basically like kind of jump ahead shortcut, you know, so you don't have to relearn those features. You can use those already learned features and then go from there. So yeah, cool. Maybe we'll talk about this next time too. Like we have our time on Thursday as well. But yeah. Okay, so I know we're much over time, but I kind of had a feeling that it was gonna happen anyway. Any last questions, concerns, comments? No? Pretty good. Okay. Well, cool. Well, we'll end it here then. Again, if you guys have questions and stuff, ask on Slack. I know this is our last week before we have break next week. So remember that, you know, don't stress out if you're like getting close to Friday. Remember, you do have time. But I would say, do try to finish up as close as possible so you do have that break week to breathe a little bit before we go into capstone and your assessment.
Okay, so you just said something that's going to make me ask another question.
So
you wrote on Slack that next Monday we're off, and that on Tuesday Tuesday we have regular class. We're off. So so is next week off or is next week not off?
Tell you what, Alvaro, you guys can show up on Tuesday. I'll be here. No, that's my bad. I have other cohorts, and I was like, oh yeah, this was a message that was put out. It's like, oh, make sure you share this message. And I realized now, I'm like, oh, that's right. You guys have break week next week. Let me double check. Yeah, you guys have break week next week. So you guys don't have to worry about that message at all. You guys have all next week off. So it's an extended long Monday or short Monday. Yeah,
something like that.
Week is gone. All right. Thank you for clearing that up too, because that is kind of confusing. I think I'll change that message to make sure no one else actually gets confused on that. All right, everyone. Well, take care, and I'll see you all around. All right.
All right. Have a good one.
I was thinking about